Hello students, today we are going to look at the topic copy on write. So before going on to that, in the last fourth module lecture, what we learned was regarding virtual memory and the concept of demand paging and what are the steps in handling its page fault. So just as a revision, all of you must remember that when virtual memory is divided into a number of fixed size blocks known as pages, and the physical memory is divided into similar sized blocks known as frames. Okay, now and to assist them the mapping, you have something known as a page table. Okay, and there are also these same blocks or whatever the process has is divided into a number of pages, and those pages are also stored in secondary storage devices. So what is the advantage of demand paging is that as per requirement only those pages will be brought into the main memory. That is the advantage of that. All the process, the entire code or all the pages of a particular process need not be in the memory all the time. Only as per requirement they'll be bought. So that is how we can reuse the physical memory frames for each and every process, thus increasing the degree of multi-programming. Because how does your system become a multi-programming kind of system? Only if a number of processes are handled simultaneously, isn't it? So if you are able to bring multiple processes pages into these frames of the physical memory, that means we are currently parallelly running multiple processes. So that is done with the help of demand paging. Okay. Now coming on to topic for today, that is copy on write. Copy on write, or COW in short, is a technique for sharing virtual memory or pages, you can say. Now it is basically associated with a system call that we learned in the beginning modules, that is fork. When we learn threading, all of you must remember that if you have a parent process and if you apply a fork system call, it will be dividing or it will be executing a copy of itself, which is known as a child process. So that was the advantage of this system call. So you can duplicate itself. So the fork system call creates a child process, and that is a duplicate of the parent. So whatever is the parent, the job of the parent, the same thing the child also will be doing. And we know how this address space is going to work. As an example, you can see here, this process, suppose this is a parent, process 1 is the parent, and process 2 is the fork of the parent, that is the child process. So what happens is, suppose that this has some page A, some page B, and a page C. And when you're creating a fork command for the parent, what will happen? A duplicate of the parent will be formed, and this will also contain page A, page B, as well as page C. So in a normal procedure thing, how it is going to work is, you'll be having page A, page B, and page C of parents. So imagine this is the pages in the physical, or the frames in the physical memory, which stores the pages of the parent process, that is page A, page B, and page C. Now, when it comes to the fork or the child process or the process number 2, it also contains the same code actually. So there's a possibility that this can be repeated. That is, child's page A, child's page B, and the child's page C can be duplicated in the physical memory. But we know it is unnecessary, right? Because the parent and child are duplicates of each other. What is the need for creating 3 different extra ABC pages for the child also? There's no need for that. Actually, these 3 pages are the same for process 1, that is a parent, and process 2, that is a child. So we can actually share them. And this is an example of sharing. That is, instead of having duplicate copies for the child, both the processes, that is the parent process and the child process, they can share the same pages. So this is page A memory for both parent as well as child. This is page B, and so on. This is for page C. So they are actually sharing these things. So that is the advantage of virtual memory, that you are able to share pages also. So copy on write is actually a different technique because of this. Now we'll see what is copy on write. Copy on write is bringing a change into the system. What is the change is that we are talking of, when you're talking of simple fork, you can say that the parent's address space is a copy of the parent's address space is same done for the child also. So that is how duplicating of the pages that belongs to the parent also now belongs to the child. But there is a possibility that many child processes, that is a forked child process, may invoke an command, an extra system called known as execute. We all already know that, and we have done it in our labs also. Exec. So that is a command for what? So that a child process. So you know that this will duplicate itself to this. Now suppose the child process is calling the execute command. What is the purpose of that? It is deviating itself from the parent's duplicate. That is, it is not going to be the same as the parent. Yes, a child is created from the parent. Initially, it will have the same code, but later on it is going to change itself. It's going to change its body, or it's going to change its code, you can say. Okay, so child process, if it invokes a exec command, then what happens is it changes itself from its parent. Okay, its code will be changed. So that is a basic idea. When such a situation come, can sharing be applicable? No, this cannot be applicable. Why? Because now the code of the child has changed. So that is why, what is copy on write? Copy on write allows both parent and child process to initially share the same pages in the memory. That is a figure that I've shown you here. Initially, they will be sharing the same pages in the memory, both of them. You can see A and B and C, as well as process 1 and 2, all the 3 pages are shared. But later at a point of time, when one of the process, it need not be the child itself, even the parent also can change its code. Okay, so if either of the process, that is either the parent or the child, modifies a shared page, ഏതേലും ഒരു process, അതായത് parent ആയാലും child ആയാലും, if it is modifying the shared page, then only that page is copied. That is, you may create an extra copy of that page so that it can be a modified version, not the original version, because only one of them is trying to change. So one of them requires the original one and the other one requires a modified one. So these shared pages will be marked something known as COW. It's like a COW page. That means there is a possibility that if there is a modification attempted on this particular page, then a copy of the shared page will be created. Okay, so it is marked as COW kind of thing. And what happens is, if either process writes or modifies, whatever it is, either it modifies or it writes onto the shared page, a copy of the shared page is created. So COW will allow for more efficient process creation, as only modified pages are copied. That is the advantage here. For example, you can see here, suppose this, I told you like before, this process 1 is the parent, and you fork this process 1 to create process 2. Now they are initially sharing 3 pages, page A, page B, and page C. Now suppose that at a later point of time, process 1, that is the parent, wants to change something in page C. Okay, so now he cannot change this original page C. Why? Because it is also being shared by the child. Okay, he cannot change the original page C. So what he can do is, this page C has been actually marked as copy on write. That means if somebody is trying to modify it, create a copy of that page. So this is the page C and this is the page C. Now he has changed something in this particular C. So a copy of this page will be created like this. So if the parent process has, or it has created or modified a change in the page C that was initially shared by both of them, then a copy of that particular this thing will be created. Now you can see the arrow has changed from here. It has changed, okay, to here. So now this page C is shared, or you can say, or used only by the second process, that is the child process. So it need not be only the child process that creates the execute command. It can also be the parent process. Once it creates a duplicate of itself, it can itself change. So that is what happens here. So this is known as copy on write. Okay. So now you can see, obviously, when COW technique is used, only the pages that are modified by either process are copied. You can see in this particular figure. Did we make any change on A or B? No, only C was being tried to be modified by the parent process. So a copy of that was created. So all the unmodified pages. So because now you can see, even though A and B and C all belong to process 1, and it tried to change process C, that doesn't mean everything has to be changed. No, those pages which are actually, it's a duplicate of itself. Only those pages that are modified needs to be changed. Rest of the common pages can be still shared between both the parties. Process 1 and process 2 is still sharing page A and page B. Even though page C has changed, it doesn't matter. The remaining pages, all unmodified pages, can still be shared by the parent and the child process, because that is how it originated from that parent. So അത് മാറ്റേണ്ട കാര്യമില്ല. ചേഞ്ച് ആയ പോർഷൻ മാത്രം മാറ്റി ഒന്ന് പോയിന്റർ മാറ്റി കൊടുത്താൽ മതി. Okay. Note to that these pages can be modified. It has to be marked as something known as copy on write. And pages that cannot be modified, there are certain pages, for example, pages like which contain executable code. In this example, I showed you pages which are allowed to be modified. So you may have certain processes where modification is not allowed. Many cases may come like that. So say for example, where you have pages which contain some executable code, that is not, you cannot allow that particular thing at that point of time. So those things, even though they are shared by the parent and child, but these kind of pages cannot be modified. Okay, these pages cannot be modified, so that is why those cannot be marked as copy or write. So it is a technique that is used in many of the operating systems like this. That is all about copy and write. Now, moving on, we have to move on to what is meant by page replacement. So just to see what is known as page replacement, just a second. Okay, suppose that you can see, all of you know what is meant by page fault. Okay, page fault in demand paging, when you're trying to access the memory, or when you're trying to access a particular frame from a memory and it is not available in the physical memory. When I say memory, it's physical memory. Okay, when you're looking for a page or a frame in the physical memory and it is not available, what is the meaning of that? You have to go and search it in the secondary storage and you have to bring it here. So that error process that occurs is known as a page fault, but that is not an issue because that is a concept of demand paging. Okay, so, but if the number of page fault is too large, then it is very difficult. Yes. So we have to try to reduce the page fault, but that is how demand paging works also. So in demand paging, what happens here is, you can see, we are trying to increase the degree of multi-programming. I already told you this in the previous session. That is why we are trying to increase the degree of multi-programming, is that is how we expect our operating system to work and the CPU to work. So that is why many processes can be loaded into the memory at the same time and they can be executed in parallel. And why? How does demand paging help in that? Because it loads only the necessary pages. It does not load everything of a process. It does not load everything of a process, except that it loads only the necessary ones that are important one for running now. And as per requirement, it goes to the secondary memory and gets the remaining pages. So that is why you have space for other processes to be accommodated also. One process page, you may not get space for other processes. So multiple process all required pages memory. That is how multi-programming can be increased. And that is a concept of demand paging. But what happens here is there is a possibility of over allocation of memory. Okay, so if as an example, you can see, suppose that we have 40 frames in memory. Okay, we have around 40 frames in memory and we have 6 processes, each of which has 10 pages. So imagine the virtual system, how it is going to look like. We have 6 processes. Okay, we have P1 to P6, 6 processes, and each of which has 10 pages. Each one will require 10 pages, but it uses only 5 at the moment. Only 5 are being used by all of them, all the 6. So you can say 6 processes into 5 pages. There are 6 processes into 5 pages. So total of how much you require is 30 pages. So 30 pages is only required at the moment and they can be fully loaded into the memory. So the remaining, the total, there are 40 frames. Okay, 40 minus 30, you have the remaining 10 frames that are free. And you can see all the 6 processes are executing simultaneously. All is fine and good. But suppose now a situation comes where all the 6 processes wants to use all the 10 pages. Currently, what we talked about earlier was we are using only 5 of them, right? So that is how it concluded up to 30. But now I'm saying it wants to use all the 10 of them, all the 10 of them, all the 6. So that is how much we require. 6 into 10. That is, we need 60 pages at the simultaneously at the same time. So all the 6 process wants to use all the 10 pages. So that means the remaining 30. Currently, we have already 30 in the memory. So the remaining of the total 60, the remaining 30 pages now has to be loaded into the memory. Total 60 ആണ്, 30 already load ചെയ്തു. The remaining 30 has to be loaded. Okay. Now, but we do not have any number of free frames. How much we have? We have only 10 frames that are actually free. Okay, so that is why the question, what happens if there is no free frame? What can we do? Okay, so as an example, you can see this. Suppose that this is the virtual memory or the logical memory for user 1 or a process 1, you can say, and this is the logical memory for a user 2. And correspondingly, for its support, you have something known as page table for user 1 and you have page table for user 2. This is a physical memory current arrangement where the initial 2 are reserved for something like monitor or something, and the remaining 2 to 7, the positions frame number 2 to 7 are free. Free means are you kept aside for user process. Now this is a secondary storage device where there are some number of pages available. Now we'll just look at each one of them and see what is there. What is the need for page replacement is what we are trying to learn. So say, so for example, in logical memory of user 1, the 0th page number contains the value h. Okay. And you can see this is 0, 1, 2, 3. Okay. Now the 0th, this thing contains a value h. So you can see here, when you look at the 0th page number, its frame number is 3. So we come to, in the physical memory, we come to frame number 3 and we can see h is available. That is how why it is valid. Okay, if it is available in the memory, we put a valid bit. Otherwise, we put a invalid bit. Now look at the second page number. It is an instruction. Instead of actually a complete data, it is actually an instruction that is to be done. So what is the instruction? It is to load M, load the data or the load the block M, labeled M. Now we'll come to this particular page number 1. We find that the frame number is 4. So when we come to frame number 4, it is also containing that instruction. Loading M means you have to load it from the secondary storage, but it is currently not there, but it is a valid instruction. And similarly, J is at 5. So this is 5 and you contain J here. Now the next one, you can see third one, that is M. It is actually not there currently in the main memory. That is why it is kept as an invalid bit. So you can say currently this is an invalid bit, or it is indirectly not a free frame exactly, but it is not being actually used. And the second one, come to the second part of the process, that is user 2 process. Similarly, here also you have the 0th page number 0, 1, 2, 3, and it is at the 6th location. So come to 6 and you find A here. Then you have 1 here. Okay, 1. The page number 1, it is actually, it is the value B, but it is currently not in the main memory. You can see it is D, H, J, A, and E. It is not there in the main memory, so it is marked as invalid. And that means you have to go and get it from the secondary storage. Okay. Now next is if a requirement for B comes. Currently it is in the secondary storage. The next is 2 and then 3. So page number 2 and page number 3 is at location frames 2 and 7. So look at 2, you have D, and at 7 you have E. Okay. So these are the things that we are trying to do. Now here you can see this load M is an instruction. Load M, sorry. Load M is an instruction over here where M is already there in the user process. It is already there in the user process, but because in the first page number again, we were trying to load this particular instruction. So that is why this became invalid. M and the value same. See, this both are same. One is trying to load it and the other one, it is imagining that it is already there in the main memory, whereas it is actually not there. It is actually there in the secondary storage. Okay, this is a basic idea. Now, okay, now the thing that we are trying to do here is we have to load this particular data, that is, or the block known as M. So in order to load it, we have to go and search in the, because the page fault occurs. Why? Because it is not actually there. Only the instruction is there. The data block is not there in the frame. So we have to go and get it from the secondary storage. When we're trying to search for it, we found it. Now we have to bring it back to the, that is swapping in and swapping out. We have to bring it back to this particular thing. But now what happens is we see that page number or frame number 2 to 7, all of them are occupied because currently the instruction is already there, right? So something is already there in every frame. You do not have even one free frame. Okay, this is known as over allocation. And now because you do not have even a single frame, even though two processes are parallelly running and you do not have a single frame, how are we supposed to load them into the main memory or the physical memory? So this is known as a need for this is a problem of demand paging, and this is why a need for page replacement algorithms comes in. Now, what are the solutions to this? We'll just see. What are the options for the operating system at this point? When you do not have a free frame, what can be done? One of the option is you terminate the user process. So when you terminate the user process, naturally many of the frames will become free. But that is not the best answer to this because it is actually destroying the concept of demand paging. Our aim is that multiple processes run in parallel, and we simply destroying whichever process is causing an over allocation. If we just simply destroy the process, it's not a good solution because then there's no need of demand paging. The second thing is the operating system could swap out a process and freeing all its frame and reducing the level of multi-program. This is actually similar to the first one. The only difference is first one was terminating the process. This is actually swapping out everything, which is equivalent to terminating. The only thing is that it's not fully terminated. It's there. You just swap out and swap out one and there no what was swapping out. You move out all those pages from the physical memory to the secondary storage device. That is known as swapping out. Okay. So you move all of them. That processes every page wherever it is. These, this, and this. All those things will be moved to the for temporary. It will move to the secondary storage, and later we bring it back when needed. That is good option in certain circumstances, but not always. Now, the next solution is what we're going to learn in the next slide, that is page replacement algorithms. That is, we have to determine from among all these pages, okay, from among all these pages, which page should be removed or for the time being, like I said before, not every page of every process or of one process, every page maybe one or two frames or maybe one frame depending on the requirement. We just have to move one page into this, right? So we may decide which one is to be selected. Say for example, I'm taking D. So D will be swapped out and in that place M will be swapped in, something like that. So we have to decide an algorithm or a strategy in which these pages can be, or some pages from the memory is swapped out and such that the required page is swapped in. Okay, so this is a need for page replacement algorithms. Okay, so we'll see what is the basic idea behind the page replacement algorithm. So the first thing is that the page replacement has basically this following approach. That is, if no free frame is available, you do not have any free frame. Okay, there is no free frame. Then what we have to do, we have to find one that is currently not being used. Find one currently not being used. Okay, and we free that location and then swap in the required one. That is the basic idea of page replacement. That is, if you do not have any free frame, you find one from the main memory that can be removed for the time being, and then you bring in the, then we bring in the contents from the swap space. So you can see we can free a frame. How do you free a frame? You can free a frame by writing its content to the swap space. What is a swap space? Is nothing but the place where you bring in temporary frames like this to the secondary storage device. Upon an area reserved and you have a reserved area like this. And what happens is then you bring it to the swap space, and after doing all these things, what you have to do, we have to update the page table naturally, because the page table contained the older frame and now you're swapping it out, so it has to become invalid. Okay, the data bit, valid invalid bit has to be changed, And similarly, you have a bringing in a new frame, so that also has to be updated in the page table. So the page that is no longer in the memory has to be marked as invalid, and so on. Okay. Now, what is the basic idea is given in this second slide. So the first thing is you have to find a location on the desired page. That is what is the basic idea for modifying the page fault service routine to include the page replacement. So the first thing is find the location of the desired page on the disk. Okay. And then you find a free frame. So if there is a free frame, suppose already you got a free frame. Search some of the pages are occupied, say C, D, and suppose you find a free frame, then naturally you can just use it. That is the first option. Now, suppose there is no free frame, then use a page replacement algorithm. That is what we are going to learn in the next lecture. And this page replacement algorithm is going to select something known as a victim frame. What is a victim frame? The person who is being selected as the person, not the person, sorry, the frame that is being selected as a frame that is to be thrown out of the memory. That is known as a victim frame. Who is going to suffer, you can say. So that is why it is a victim frame. So write the victim frame to disk. So you write this particular victim frame to the disk. And what you have to do accordingly, you also have to do, I'll tell you what is this dirty bit. It's coming only. So there's a concept known as modified bit or dirty bit. So you have to write the victim frame to the secondary storage device, that is the swap space. Then you change there's one more thing you have to do. You have to change the, the frame tables as well as the page tables. All those things have to be. Frame tables we have not actually learned in detail, but they are also existing. We have learned only about page tables. Okay, keeping track of all the free frames or the allocated frames is something known as frame tables. So that also has to be updated. So write the victim frame to the disk and make these required changes. Now, the next thing is that changes is also done here. Change frame tables plus page tables. Both have to be updated. Now, the next thing is bring the desired page into the newly free frame. So we found one free frame, right? We used it. If we did not find any free frame, we select a victim frame and we move that victim frame to the secondary storage device. Now your frame is free. Suppose this was not free, then we move this part to the secondary storage device and we make it free. Okay, we make it free. Now, once it is free, you bring in the desired page. So that is from the secondary storage, we are going to bring in a page. So that is known as swapping in. Now update the page table and the frame table again. Why? Because we are bringing in something new. So instead of the earlier invalid bit, now something new will come and we make it valid. Now continue the user process from where the page fault was occurred. So wherever the user process found a page fault, this entire situation was being done. And now once it is over, we continue the process from that point. Okay. So this is what is bugged. Now, what happens here is that because if no free frames are available, look at this step. If no free frames are there, then you are actually requiring two page transfers. Why? One is transferring one victim frame out of the memory, and the second one is you're bringing one from the, that is where, why? Because the page fault occurred for some other reason, right? ഏതോ ഒരു പേജ് ആവശ്യം വന്നപ്പോഴല്ലേ page fault വന്നേ, and that second page has to be brought in. So two page transfers has to be done in this case. So what happens is you are effectively doubling the page fault service time. You know what is meant by a page fault service time. So you are doubling the page fault service time. I told you page fault is necessary for demand paging, but if you have a lot of time just for always you're getting the page fault, then that means that your system is going to become slow. Okay, so what you have to do is we have to increase the effective access time. That is what is in short form it is written, the effective access time. Okay, effective access time has to be increased accordingly. That is a ശരിക്കും ആക്സസ് ചെയ്യാൻ വേണ്ടി നമ്മൾ effectively എത്ര ടൈം നമ്മൾ യൂട്ടിലൈസ് ചെയ്യുന്നു എന്നുള്ളത് കണ്ടുപിടിക്കണം. So that is the requirement here. Okay. Now we can know that is we can overcome this or we can reduce this particular overhead by using something known as a modify or a dirty bit. To reduce the overhead of page transfers, we are introducing something known as a modify or a dirty bit. So what is the meaning of that is only modified pages are written to disk. For example, suppose that this is the main memory and this is the physical storage, and you found a page, say it contains a data D, and that is actually also there in here. We initially before any time before this, we had actually copied it from the secondary storage and we brought it to here. Now suppose that a request for a frame M comes. Okay, a request for page M comes in, and you find that M is only there in the secondary storage. See, M is only there in the secondary storage. It is not there in the physical memory. It is not there in the physical memory. So what happens? A page fault occurs. Okay, it is not there in the physical memory. So what happens? That is something known as a page fault. Now we have to find a victim frame. So suppose that I found that this is the victim frame. Page replacement algorithm, you say that we have to find a frame that can be replaced. So what I'm going to do, I have to write this somewhere to a swap space in the physical memory, in the secondary storage device, and I have to make this free. So when I make this free, this is going to be like this, right? Find a victim frame and write it to the disk. Understood? So select the victim frame. For example, D is the victim frame. I have to write it back to the disk. You know that a copy of D is already there in the secondary storage, because from there only it was copied initially to the main memory. Requirement secondary storage, then only we bring it to the main memory, right? So actually a copy is there, but we are not just accessing it. That's all. So for D to execute, it has to be brought to the main memory. At a later point of time, I decide that D has to go back. So if you can make now what you have to do is you have to write it back to the location. So now what is the purpose of this modify bit or dirty bit is that you can decide whether this particular frame in the memory, this one D, has been modified recently. If it has not been modified, it will contain the same copy that it earlier had in the secondary storage device. അതായത് ഡി നേരത്തെ സെക്കൻഡറി സ്റ്റോറേജ് ഡിവൈസിൽ എങ്ങനെയായിരുന്നോ കിടന്നിരുന്നത് അതിനെ ഞാൻ ഇങ്ങോട്ട് കോപ്പി ചെയ്തു, അതിനെ എക്സിക്യൂട്ട് ചെയ്തു, ബട്ട് ഐ ഡിഡ് നോട്ട് മോഡിഫൈ ഇറ്റ് മേ ബി, ഓർ ഐ ഡിഡ് നോട്ട് മേക്ക് എനി പർട്ടിക്കുലർ ചേഞ്ചസ് ദർ. You can imagine that way. Some piece of code that was already there in the hard disk, I brought it to the main memory for execution, but I did not modify it. So if you did not modify it, then what is the need for writing it back to the to the secondary storage? From the main memory, is there any need to write it back to the secondary storage? No, because the copy already exists. Same sanam pinne write cheyidittu valla karyam, there's no need. So what you can do, you can discard it. Why? Because it is already there in the secondary storage. So how do you know whether it has been modified or not? You keep an extra bit here. That is what is we have written here, a modified bit or a dirty bit. Look at that, a modified bit, a modify bit or a dirty bit. So that is what we are trying to do. So what is this modify bit or dirty bit? Every page or frame has a modify bit associated with it in the hardware. Now, what is this for? It is set by the hardware such that if any byte in the page is written, just to indicate whether anything has been written into it, indicating that the page has been modified. If it has been modified, then naturally this particular thing will have to be written back to the swap space. If it is not modified, you just discard it. So that is the purpose of modify bit. Okay. So we'll just look at the steps of basic. This is the steps which I taught you now, and we'll look at it with an example. Okay. Suppose this is a page table, and we need to find, or we need to swap something into the physical memory, and you do not have any free frame. Imagine there is no space in the physical memory. All of them are full. Okay. So the first thing we have to do is we have to assess, and using a page replacement algorithm, we find a victim frame. Say F is a victim frame. Okay, so now we swap out the victim page. We swap out the victim page like this. Okay, and the next step is, because something from F was already swapped out, we made that indication as 0 and we set it to invalid. For the invalid aaki koduthu. Why? Because in the invalid akana, because our frame in memory illa, it's not there in the memory anymore. Now what is the next thing? this is a page that is to be brought in, say M. Okay, now what we bring it to the memory over here. Now it is in the as a new F. Okay, instead of this victim, when now it is free, we bring in the desired page. Once you bring in the desired page, what is the next step? The next step is you reset the table for the new page. So now F is added into the memory. You can say this is a change that is going to occur, maybe in the same location, and it is set as a valid bit. So these are the steps to be done in a page replacement algorithm. Now we can improve the situation by adding something known as a modify bit or a dirty bit. Modify or a dirty bit. Now what is the purpose of that bit? What is the purpose of that bit? That is this victim frame that we selected here. This victim frame that we selected here. Do we have to write it back again to the secondary storage? That is what we are trying to do. Do we have to write it back to the secondary storage? If not, if that swapping out can be avoided, we can save the time. Okay, so this is the complete situation of how a page replacement works. So I hope it is clear. There are algorithms for frame allocation also. There are algorithms for page replacement also. So we'll look into this in the next lecture. Thank you.